Okay, good morning, everyone. Good morning, class.
Good morning, Miss.
Thank you.
Good
Today
morning.
we will be morning. How are you guys?
Fine, miss. How are you?
I'm good, thank you. Okay. Today will be our third tutorial. Okay, and before we start, I would like to remind on the uh course assessment 2. Okay, for course assessment 2, it is on your experiment report that we have conduct in, I think, a couples of weeks ago. Okay, for those who have conduct experiment in UTM KL with me, okay, please summarize all the results that we have got during the experiment. Okay, and then put it in very presentable report. That one will be the course assessment too. For those, please ensure that you gather all the results from your friends as well. Okay, because we have grouping sessions on the day. Okay, for those who attend the experiment in UITM Penang, okay, your instructor contacted me and informed that there are one of the parts, the final one, right? The final one is not all of you get the result for that. And not to worry, you may discuss whatever result that you have in the report. Okay. Because of that, I will not deduct marks. Okay. But then depends on your discussion. Okay. If you discuss well, then you akan dapat markah yang tinggi lah. Okay. And for those who did the experiment last week, online simulation, same with the physical lab, you need to put all your results, the online simulation result in the report, and then discuss if there is any calculations that you need to attach, then put it in the report as well. Remember, yeah, guys, for the course assessment 2, there will be no extension. Okay, no extension for course assessment 2, meaning that you need to submit before the deadline. Okay. Any questions on the course assessment 2? All good? Okay. Okay, thank you. All right. So today we will go for the power amplifier. This one is the final part in our analog electronic. Okay, this is our final class too. Okay, we have two objective here to explain on the Q-sense Q point, and also we have different classes of power amplifier. We will go on that one later. Okay. All right, this is on the Q point. And for the power amplifier, we have class A, class B, class AB, and class C. Actually, there is also more than this 1, 2, 3, 4. We have class D, I think. But then for our syllabus, we will only cover until class C only. Okay. All right. So before we start, let's go for this one first. What is actually large amplifier? Okay, we have discussed on we have learned on the small signal amplifier. Okay, in fundamentals of electronic. Okay, we have learned on the transistor and on the AC analysis. That one is on small signal amplifier analysis. Okay. For the large signal amplifier, it is designed to amplify signals with high amplitude. Okay, normally when we have handling a very large values of in terms of the powers or voltage input, Okay, mainly used in applications where large voltage or current swing are required for the output port. Okay, this amplifier operate same goes with the small signal. It is nonlinear regions of the transistor's characteristics. Okay, and where is the applications for this large signal amplifier? Normally, we apply in the audio amplifiers for power amplifiers of the speakers, and also for the communications field for radio frequency RF transmitter, because we want to transmit large signal amplifier over very long distance. And also we use in a switching power supplies where large current are needed to power devices. Okay, for the high power output, deliver very high power to the load. For example, if we apply in audio amplifier, okay, in the speaker in audio systems, also for the transmitter for communication system. Okay, in essence, large signal amplifiers are crucial for applications where high power and efficient energy transfer are essentials. Even in some signal distortions is acceptable. Okay, for the types of large signal amplifier, we have these classes by the power amplifier. We have class A, class B, class AB, and class C. Class A we have with the high linearity and low distortions. And this is the lowest efficiency, around 25 to 30% only. Class B, better than class A. The efficiency is around 50%. Introduce the crossover distortions. This one is as we have conducted in the experiment. Okay, class AB balances efficiency and linearity, but that one is widely used in audio amplifiers. And class C is has the highest efficiency in the from these four amplifiers, and mainly we use in RF FP applications. Okay, for this efficiency designed with the amplifier designed with the efficiency depending on the applications. Okay, for then large signal amplifiers are powerful amplifiers intended for applications requiring substantial power output, commonly found in audio system, in transmitters for communications, and also in the high power equipment. For the designs, emphasize the efficient power delivery and handling large values or amplitude for current and voltage variations. Okay, next one we go for the cue point. This one, I will share these notes with you guys after this class. I'm sorry, I forgot to share this one before the class. Okay, for this cue point, it is the critical operating point that sets up an amplifier performance by establishing initial DC conditions, meaning that this one is from DC analysis. Okay, importance of the cue point is to minimize the distortions and also for the temperature stability. We don't want the signal to be fluctuate. The steady state conditions for the cue point is established when there is no input signal, only DC bias is applied, meaning that it represents the resting state of the amplifier. Okay, I think I have the notes in my phone. Wait, yeah. Oh, no, already delete. I will share after this. I will share after, okay. I will share after this class lah. Okay. And the cue point also determines how the amplifier will respond to the input signal. We want to get the output, but then we need to respond to the input signal. Okay, by setting the input signal properly, the amplifier can handle for both. We have positive and negative swing of the input signal without distortions. And we have active region for linear amplifications, the Q point should be in active region, allowing the output to vary linearly with the input. For cutoff and saturation region, that one is for switching of applications on and off conditions. The Q point is moved to cutoff saturation where the device operates in the on and off condition. Okay, Q point placement in different amplifier classes. We have class A set in the middle of the active region, for class B at the edge of the active region, and class AB is slightly above the cutoff, and for class C below the cutoff. For the Q point is the critical operating point that sets up an amplifier's performance by establishing the initial DC conditions for optimal signal amplification with minimal distortions. Proper Q point selection is essential for ensuring linearity, efficiency, and stability in the amplifier circuit. Okay, let's see on this one is the AC and DC load lines. Okay, we have combined AC and DC load line. As you guys can see, this is this line. Okay, this is the AC line. This one, meaning that this one is the AC and DC lines. Okay, this is for DC. And the cross between the two lines will be the Q point. AC and DC load lines are graphical tools used in amplifier circuit design to help analyze and visualize the operating conditions, such as for the Q point. Okay, and for the DC load line definitions, the DC load line represents all possible combinations of we have the collector current as the y-axis, and the collector emitter voltage for the x-axis for a transistor circuit when considering on the DC power supply and DC resistance. The purpose of the Q point of the AC and DC load line is to establish the Q point. We want to get these locations for the Q point. For a transistor in the amplifier, we apply the transistor. We use transistor in the circuit by showing where the device will operate with no AC signal applied. Okay, and for graphing on the DC load line plotted on the IC and versus the VCE. Okay, the endpoint of the DC load line when we calculate for either this one VCE is equals to 0. When VCE equals to 0, then we get this point, maximum IC. And then this one is when we open circuit at the IC is equals to 0 when open circuit. So we have the VCE at the maximum. So when we have these two, at this is VCE equals to 0. Okay. Short circuit is VCE equals to 0. So we have this line for the DC analysis. Okay, straight line is drawn between the 2 points and the Q point is ideally positioned somewhere in the middle. The Q point must be somewhere in the middle with the intercept of the AC load line. Okay. For the AC load line represents the transistor's operating conditions under AC signal variations. It takes into account for both DC load resistor and for DC load resistor, normally it is either RC and any additional impedance due to the AC signal path. Okay, and for the purpose of the AC load line, it shows how the transistor will behave dynamically as the input signal varies. Okay, indicating the maximum possible swing of the IC and VCE value during the amplifications. Okay, how to plot for the AC load line? Plotted on the same graph, we have the IC and VCE, but with a different slope. Okay, as you guys can see, this one is more steeper, ini lagi curam lah. Okay, the slope for the AC load line is determined by the total AC impedance seen by the resistor, which can be different from the DC resistance. For this is for DC, and this one is for AC. So due to the resistance, the slope will be different. Okay, the slope of the AC load line is determined by the total AC impedance seen by the resistor and different with the DC line. Okay, the AC load line is usually steeper than the DC load line because the AC load line may be lower than AC resistance might be or normally lower than the DC resistance. And significantly, the AC load line shows the range over which the transistor can amplify the input signal without distortion. It is crucial for determining the output signal swing and ensuring the amplifier operates within a linear region for a maximum operation. Okay, so this is an example of the Q point for common emitter amplifier. And this one, the A is the small signal amplifier of the common emitter. To relate the small signal model with the AC and DC load line, then we need to focus on understanding how the small signal parameter, this one, and the output resistance, okay, for the Q point and DC load line. Okay, we have here the DC load line, AIC versus VCE. Okay, the DC load line sets the Q point. The small signal model linearized around this Q point for small AC signal. And the AC load line limits the maximum signal swing and defines the effective load resistance seen by small signal model influencing on the gain. Okay, and then we need the proper biasing for the Q point positioning, ensuring for small signal model remains valid by keeping the amplifier, this the whole amplifier in active region for linear amplifications. Okay, and then by combining on the load line for biasing of the AC and for signal swing, we can accurately use the small signal model for predict amplifier performance for small AC input. Okay, that is important of the understanding for the small signal amplifier or small signal analysis. Okay, this is the Q point. Okay, we have here is the DC load line, the red one, the blue is the AC load line. The difference between AC and DC load line. For DC load line, only considered on the DC supply voltage and DC resistance, and we used to set these two actually used to set for the Q point. And for AC load line, the blue one, considered the AC signal impedance shows the amplifier's response for the input signal. Okay, the amplifier AC signal impedance is the RC. Okay, the RC we have here. Okay, this one is which connected to the DC supply. Okay, the intersections of the DC and AC load line represents the operating region for dynamic conditions, the Q point. We call it as the Q point. For optimal performance, Q point is set to the signal can swing equally around within the limits of AC load line. And then by using for both load lines, AC and DC load line, we ensure the amplifier can achieve maximum output swing with minimal distortions while maintaining stability. We want the amplifier to be as stable as it can perform the best accuracy, at maximum and at the optimal efficiency. Okay. So next one, we go for the power amplifier that we have. Okay, it is basically the large signal amplifier, which is different from the small signal amplifier as earlier we have discussed. Okay, for The analysis of power amplifier is not the same as corresponding to small signal amplifier counterpart. Okay, power amplifier normally used as final stage of a receiving or transmitting system because the purpose is to amplify the signal. It can be used to provide signal power to speaker of typical 4 ohms resistance or to transmitting antenna around 300 ohm resistance. And ideally, power amplifier would deliver 100% of the power it draws from the DC supply to the load. But that one is in ideal conditions. But in practice, in actual one, this can never occur because some components of the amplifier have the dissipating factor for dissipating power. Okay, and we have the power efficiency. The symbol for power efficiency is equals to AC output power over DC output power multiplied by 100. Okay, so we have the P out over PDC. P out is the PAC. Okay, multiplied by 100. That one will be on the power efficiency. Okay, first we go for the class A power amplifier. Okay, as you guys can see here, we have the input of class A and this is the amplifier. Okay, what is the difference between the input with the output? Okay, when an amplifier, irrespective of common emitter, common collector, common base configurations or transformer couple is biased with an input signal such that it operates in the linear region for 360 degree of the input cycle. That one we call it as the class A amplifier. Okay, first we look at the amplitude. Okay, the amplitude, it amplifies the value of the signal, but it change on the phase, on the degree. This one first is on positive cycle, but now it become the negative cycle. So this swing. Okay, same goes for the second one. This one become positive. Okay, that is the purpose of the class A power amplifier. Okay, this is examples of circuit for class A amplifier. This one is common emitter amplifier. Okay, the DC and AC load line of this amplifier are different because they do not have the same equivalent circuit. Okay, for class A power amplifier, the most common one. Okay, and for the power amplifier, we can get on the voltage gain. The voltage gain of class A amplifier is determined the same way as the small signal amplifier with the exceptions of the formula use AC emitter resistance for the small RE. Okay, small RE is not valid for large signal amplifier. So we are not considering on the small RE, this one. Okay, and for this equations, the expressions with bypass capacitor at emitter resistance. Look here, we have this C3. So when this one short, current will not flow here. So bypass RE. There is no RE in the voltage gain here. Okay. So for this one, replace with this one here. Okay. And we have the power gain. Okay, we have the AV, voltage gain, AI, current gain. So for power gain is equals to P equals to I multiply with V, right? So for power gain equals to gain of the voltage multiply with the gain of the current. So we have this power gain. Okay, where for large signal current gain AI is approximately equal to DC beta, beta DC, and also alpha RC over RE. Okay. This is, for this one here, is the power efficiency. power efficiency of the class A amplifier. Remember from the previous slides, not this one, not this one, this one. Class A is around 25, class B is around 50, next one is around 75. Okay, around AB, class AB or class C. We will see. Oh. Okay, so for class A, I can say that for all calculations, it must get in between 25% to 30% only. For class A, this is the characteristic of class A. Okay, this is also on the maximum power efficiency of class A amplifier since P out is a maximum power. Okay. Okay, in order to achieve higher power efficiency for class A amplifier, we put it transformer coupled class A amplifier can be designed. Owing to the presence of counter EMF in the transformer, then the AC VCE drops to minimum value. The voltage across the primary coil is equals to VCC. Okay, and this one also on common emitter amplifier class A. The DC resistance of the primary coil is normally very small, which can be less than 5 ohm. And then the value for RE is normally small for power amplifier, must be in a very small value. The voltage at collector of the transistor is approximately equal to 2 VCC. And this ideally the AC VCC is equal to 2 VCC and also AC IC saturations equal to 2 ICQ. And then the DC VCQ is approximately equal to the VCC value. Okay, and this is when we have the transformer class A amplifier coupled with the transformer. Okay, and for the efficiency, we can get until 50%. Ignoring on the current flow in the voltage divider network. Okay, we have voltage divider this one. So we can say that for this I is approximate to 0 because on the very small value. Okay, maximum AC power for the P out, we can say half of the VCC ICQ or equals to half VCEQ ICQ. And for the DC supply power, for PDC, VCC ICQ. So this is the efficiency for class A coupled with the transformer. Okay, next one, we go for class B power amplifier. This is the input and this will be the output for class B. Okay, when we inject this input, go through class B, we can get this output. Okay, it is different with the class A amplifier. Okay, when an amplifier is biased such that it operates at the linear regions for 180 degree of the input cycle and is in cut-off regions for net 180 degree, then we call it, this one is a class B amplifier. Class B is biased at cut-off region so that the ICQ is equals to 0. And for the VCEQ is equals to VCE cut off. So 480 degree of the input cycle. So it only amplify on this signal sahaja, not for the second cycle. Okay, only on the positive cycle, but then a very large value of the amplitude. Okay, let's see on the circuit for class B. Okay, we have two circuit for class B. This is for positive cycle and this is for negative cycle. Okay, this one we have this positive cycle. If you want to amplify on the negative cycle, so this is for the second negative cycle. Okay, we have two transistor here, Q1 and Q2, so that one will be on and off accordingly. One will on for positive cycle and another one will off. For negative cycle, one will off, then Q2 will be on. Okay, this circuit shows the push-pull class B amplifier which utilizes two emitter follower and act as complementary amplifier. The reason for complementary is because one NPN, this is Q1 is NPN, Q2 is PNP. Okay, one NPN and the other PNP which conduct can opposite alternations of the input signal. During the positive cycle, the NPN transistor is conducting while PNP, the Q2 is off. During negative cycle, PNP is conducting, the Q2 conducting, and NPN Q1 is off. So we have this for positive and negative cycle. Let's see on the output. Okay, this is when no DC bias for the amplifier circuit, the positive cycle of the input signal need to exceed VBE. What is the value for VBE? Is 0.7 voltage. Okay, this one minus VBE is minus 0.7 lah. Need to exceed the value of the NPN before conducting can occur. Likewise, the voltage of minus input cycle needs to be less than VBE before the PNP would conduct. Okay, so we have this conducting of Q1 and this one is Q2 off. This is for Q1 off, Q2 for conducting. But then in between we have the crossover distortions. That is why for the signal dia macam lari sikit. So this part will be on the crossover distortion, this one. Okay, there is a period of the input signal where there is no conductions for both NPN and PNP, which we call it some as the deadband. The period of the time would cause on the crossover distortions. This period lah for this one. Okay. That is why for the signal it is not as smooth as the input due to the crossover distortion. Okay, next one is on the class AB amplifier. Here we have class AB common collector configuration. Okay, this one is common collector. Class AB amplifier is biased to conduct slightly more than 180 degrees and also utilizes two transistors where alternatively turn on and turn off. We have Q1 and Q2 in the circuit. Same for the voltage divider and also for the diode clamp Q1 and Q2. Okay, this is the reason it is also named as the push-pull amplifier. One of the techniques is to make both transistors slightly above cut-off when there is no AC signal and can be achieved by voltage divider technique as this the first circuit for voltage divider. However, for this voltage divider arrangement, is difficult to maintain due to value of the VBE or VEB variation caused by the temperature. And a stable technique called diode clamping, the second circuit, because the characteristic of the diode closely match with the transconductance of the transistor characteristic. So we introduced two diodes in the circuit D1 and D2. Okay, because we want to cater the value on the VBE and or the VEB 0.7 value. Okay, this is the expressions for the class AB amplifier. Okay, the DC input PDC is for the PDC is equals to VCC ICQ. Okay, and this is since VCEQ is VCC over 2, so we have this PR. For each transistor is only drawing current for a half cycle. Therefore, the current is half wave signal with an average value of the ICC equals to IC saturation over the pi because of one half cycle. And for the PDC, also we can write it in terms of VCC IC saturation over the pi for one half cycle. Okay, for the efficiency of class AB amplifier slightly higher. Okay, for a nonlinear class AB push-pull amplifier where VCE saturation is not equal to 0, okay, then we can have the power efficiency of the amplifier PDC, VCC, ICQ, and each transistor only for half cycle. Then this one we have the ICC saturations, and this one VDC. This is the maximum value for class AB can get. Okay, efficiency for class AB 78%, around that. Okay. Okay, next one we have the class C power amplifier. Okay, this is biased so that the conduction occurs for much less than 180 degrees of the input cycles. This is the input and this will be the output of class C power amplifier. As you guys can see here, it only amplified the signal at very narrow band. Okay. For these applications of class C, normally we use in RF transmitter for communications, also for the broadcast and in the RF signal generator. Okay, we apply in the RF amplifications. In the oscillator, ability to provide high gain at this very specific frequency because only amplify at a very narrow band. And in the medical equipments, devices that requires RF energy such as certain types of uh, devices, machines for therapeutic healing of the body tissue, for example. Okay, let's see on the circuit of class C amplifier. Okay, this one is a basic class C amplifier. Okay, it is by low cut off with the minus VBB supply, and the input AC source voltage has the positive peak value slightly greater than VBB value at the VBB modulus maximum value plus the VBE. Okay, so that the base voltage exceed the VBE of the transistor for a short time because we want to be exceed of the 0.7 VBE value. Okay, near the positive peak. When the transistor is total cut off during negative cycle of the input signal. Okay, let's see on the signal. Okay, this is a class C power amplifier output. Input and output, the power dissipations of the transistor in class C amplifier is low because the transistor is turned on only for a small percentage of the input cycle. It is only turned on for a very narrow or short band of the frequency only. And this collector current pulses and the time between the pulses is the period T of the AC voltage. So in between we have the T1. So from here to this one is the T2. Okay, from this one to here is T3 for one cycle. Okay, it is actually from here to this one only for one cycle. Okay, so this is the waveform output of the class C amplifier. Okay, for tune, this is for tune class C amplifier. Owing to the fact that the collector voltage is not the replica to the input signal, the resistivity load class C amplifier alone is of no value in linear applications. It is therefore necessary to use class C amplifier. We put it with the resonance circuit, or we call it as this one as the tank circuit. Okay, the short pulse of collector current on each cycle of the input initiates and sustains the oscillations of the tank circuit so that the output sine wave voltage is produced as you can get this one. If this is from input, so we can get this output, the reverse operations. Okay, we have this tank circuit here. All right. So for this class C amplifier, okay, owing to the charging and discharging of the capacitor, we have capacitor C2 in the uh, tank circuit through the inductor L. The peak-to-peak output voltage is approximately equal to 2 VCC. Okay, since the voltage developed across the tank circuit has a peak-to-peak value of approximately 2 VCC, then we can have the maximum output power for the class C amplifier. And for when the class C amplifier, when the P out is much more greater than PD average, then we can say that efficiency of class C amplifier is almost 100%. Okay, so class C amplifier is the best if we have this tank circuit together in the amplifier. Okay, so that is the end of our slide today. I will share this slide after this. Is there any question from you guys? If there is no further questions, thank you.